You've known how to do this kind of problem where you multiply out all the terms for a long time. You probably do it in one of these two ways. Either you use FOIL, which is an acronym that tells you the order that you multiply the things in. So the first terms times the outer two terms times the inner two terms times the last two terms. And when you add up all of those multiplied pairs, you get that. And if you were going to simplify, you'd get 3x plus 2. Or you use the area model. For the area model, you think about x plus 2 as describing a length. So this would be length x, this would be length 2. And when you add them together, this entire length is x plus 2. This is length x, this is length 1. And then if you're multiplying this length times that length, it gives you an area. But that area must be the same as the area of all of the parts that make it up. So now I can say x times x. So length of x times length of x gives us an area of x squared. The area of this box would be 2x. The area of this box is x. The area of this box is 2. And you add them all up, and you get the same thing. So that's stuff I assume you know already. What if you needed to expand two things, each of which were 4 terms long? Could you do that? Well, not if you've just memorized FOIL, because FOIL doesn't really apply here. Could you use an area model? Yeah, you could. This area model would describe this length as a plus c plus a plus b plus c plus d, and then this length. And you just same idea. You'd multiply everything out, and you'd add up all the small areas to get the overall area, which seems like a lot of work and not something that I want to do right now. The underlying pattern that the area model is intended to capture is the idea that when you multiply out these two expressions, you're multiplying each term here by each term here. So what am I saying? I'm saying take each of these terms, so let's start with a, and you'd multiply a by each of those terms. So you do a times e plus a times f plus a times g plus a times h. But then you need to move on to b, because it's a different term. And so you need to do b times e plus b times f plus b times g plus b times h. And then c times e plus c times f plus c times g plus c times h. And then d times e plus d times f plus d times g plus d times h. So it's each one of these times each one of those. And that's what produces your multiplied expression. There's a reason that I'm not writing it all out, because the goal here is not to have you mechanically produce, some fully multiplied outputs, but it's to think that once you understand this underlying pattern, that each of these gets multiplied by each of those, now you can very flexibly pull in and out and rewrite multiplied expressions like this, and that's the real goal. So let's start digging in with a somewhat smaller example. Using the rule that I said, you could, of course, multiply this all the way out. But you don't always want to do that when you're working with algebra. Like, you want to be able to flexibly rewrite this in different forms, because you may need to simplify in different ways. You may need to split terms in different ways in order to do what you want to do. So I'd said that you could multiply this out by multiplying a by all these things, and then by multiplying b by all these things, which looks like this. But you might notice that when I said verbally a times all these things, it produced this. And another way of saying that, and another way of writing that, would be factoring the a out. So literally saying a times all these things, c plus d plus e. And then to that we'll add b times all these things, which is the same as b times c plus d plus e. So you could multiply it all out and then realize that you can factor out the common terms, and so now you've grouped them. So this is almost like factoring by grouping in reverse. But you don't have to do this intermediate step. You could just think that if what you're really doing here is multiplying each of these by each of those, one way of imagining that is take a times that entire thing plus b times that entire thing, and that's what you get. You know that triangle times square is the same as square times triangle. It doesn't matter what order you multiply, that order of multiplying doesn't affect the final answer. That's called being commutative, and it's actually not true for all mathematical things for which multiplication is defined. Later on, you'll come across things that you can multiply where this fact is not true. But for now, commutativity is true. So all this is to say that this expression on the left is the same as the expression on the right. However, if you apply the same kind of thinking, multiply each one of these times each one of these, this will let you immediately expand this out in a different ordering. So if I'm expanding it out, I'm saying C times each of the A and the B plus D times the A and the B plus E times the A and the B. And that's the same as the thing that we wrote the first time. So that's the same as A times C plus D plus E, plus E, plus B times C plus D plus E. Okay. So you can see, like, each side here is just a different way of thinking about multiplying each thing here by each thing there. On the left, we're thinking about each thing from the 3-term expression, times A plus B. On the right, we're thinking about each thing from the 2-term expression, times the entire other expression. And those two things are equal. So what if you wanted to simplify something like this? I see that there are p's, and I see there's x's and y's. So a reasonable thing you might want to do is to separate all of the p's to one side of the equation and keep everything else on the other side of the equation, depending on what you're trying to do with this. So one thing you could do is like multiply this entire thing out, which isn't so bad. It's just p times each of those. But you don't actually have to do that. You could think, okay, I'm multiplying p by each one of these, but all I really want to do is pull out the p term so I can move it somewhere else. So rather than multiply the whole thing out, well, let me show you the slow way first. So let's multiply the whole thing out. So now I've multiplied the whole thing out. Now I can move this. Remember, I want to move all the p's to one side. So what I could do is I could move everything that doesn't involve x and y to the other side here. And then I could realize that on the left-hand side, both terms have a p, so I'd factor out the p again. So now you see I've done both those steps. I've subtracted 5p squared plus 2 on this side, and here I've factored out the p to produce this. And now I can divide by p on both sides, and that gives me what I was aiming at, which is separating out all the p's. So I've got the same thing divided by p. But my point is you don't need to multiply that whole thing out. You can think, all right, if I'm multiplying p by each of those things, that's the same as saying p times the first two things plus p times the last thing. So all I've done is I've just pulled this thing out from the inside of what I was multiplying, and that's saved me a medium amount of work in this problem. And now I can just move all these things over to that side and divide by p, and I'm done. Mathematicians are always trying to generalize, which means solving all of the problems all at the same time instead of fiddling around with individual cases. So to a mathematician, both of these problems really are the same. What you have is you've got a polynomial times a polynomial. And so maybe instead of fiddling around with individual examples, you want to ask, what's the overall pattern whenever you multiply a polynomial by another polynomial? So the general way you could write that out is write the general form for an nth degree polynomial, multiply it by another nth degree polynomial. If you multiply each of these things by all of those things, you'll end up with a whole bunch of crazy terms. But each of the terms will have some particular power of x, and so then you can group them all together. And you'd have a constant term with no x's, and you'd have a linear term with which is what you'd get when you add up all of the single power of x terms, and so on. And what is inside each of these little biscuits? It would be all of the coefficients that you'd get for your single power of x terms when you multiply all of that out. So you'd have some number of a constants and some number of b constants organized in some way. So I only wanted to pose this problem for you because this is the true mathematician's question. And it's good to be able to think of the question that is the right mathematical question to ask. That often humanity is stuck on a problem for hundreds of years until someone figures out the right way to ask the question. So if you're curious, you can fiddle around with this a little bit. You might end up inventing one of the most important theorems in mathematics. It's a really generally useful theorem applied everywhere that has to do with the pattern that happens when you multiply out two nth degree polynomials.